Hello everyone, in this video I am going to examine and compare running times of Quicksort and Heapsort algorithms. Both of these algorithms sort input array of numbers. For those who don't know, I am going to explain how exactly Quicksort and Heapsort work. First, take a look at Quicksort algorithm. The most important part of it is partition procedure. At the current image, part A, we see the operation of partition on a sample array. Array entry A of R with value 4 becomes the pivot element. Tan array elements all belong to the low side of the partition with values at most the value of pivot element, which is 4. Blue elements belong to the high side with values greater than 4. White elements have not yet been put into either side of the partition, and the yellow element is the pivot. The partition starts from the first element with value 2 and swap it with itself because it's lower than pivot element. Index I points to the last element of lower part of the array, and index J points one element past higher part of an array with elements higher than the pivot elements colored blue. If element at J index is lower than the pivot, then elements at indexes I plus 1 and J are swapped, and I and J gets incremented. If element at J is higher than the pivot, then J gets incremented. The last step is swap pivot with element of I plus 1, which is first element of the high side of the partition. At B subpoint of the image, we see regions maintained by the procedure partition on a subarray A of P to R. Tan values in array A of P to I are all less than or equal to pivot value. The blue values in array A of I plus 1 to J minus 1 are all greater than the value of pivot element, and the white values are unknown. The Quicksort algorithm performs partition of an array and then recursively call partition on low side array and another partition of high side array, which is shown at C subpoint of image. Let me explain how Heapsort works. Heapsort uses max heap data structure. At the current image, we see max heap as a binary tree and an array. The number within the circle at each node in the tree is the value stored at that node. The binary heap on the left is nearly complete binary tree. The tree is completely filled on all levels except possibly the lowest. Each node's value is greater than its child nodes. For example, the value at node 2 is 14, which is greater than node 4, which is 8, and node 5, which is 7. Heapsort algorithm, in addition, uses procedures parent, left, and right, where parent of a node I is I divided by 2, left is I multiplied by 2, and right I multiplied by 2 plus 1. For example, parent of node 4 is node 2, left of node 4 is its left child node 8, and right of node 4 is its right child node 9. Next picture shows the procedure max heapify. It's used to maintain the heap property. Its inputs are an array A with the heap size attribute and an index I into the array. When it's called, max heapify assumes that the binary tree rooted at left of I and right of I are max heaps, but that A of I might be smaller than its children, thus violating the max heap property. Max heapify lets the value of A of I float down in the max heap so that the subtree rooted at index I obeys the max heap property. Current figure illustrates the action of max heapify. The node that potentially violates the max heap property is shown in blue. Here at index 2 with value 4 is compared to its children with value 14 and 7. If blue node contains largest value, then the max heap property is maintained and algorithm ends. If not, the largest values of its children is swapped with node with value 4. Here it's 14, which is greater than value in the right child 7. Procedure continues possibly to the left, after we have sub-tree rooted of I, maintaining max heap property. At the next figure we can see build max heap procedure. It calls heapify for every node starting at first non-leaf node. Here it's node with value 16. Then calls heapify out node with value 2, so on, and finally for the root of a tree. After this procedure terminates, the whole tree maintains max heap property. The next picture shows the whole Heapsort algorithm. First it calls building max heap, which is shown at a subpoint A. Then it swaps the root with value 16 with last leaf with value 1 and decrease heap size by 1. Now at the last element of array representing heap we have the largest value 16. Next we call heapify on the root of the tree, and next maximum value element is in the root, which we swap with the last element pointing by heap size, which was decreased in previous step. Now we decrease heap size and call heapify on the root value, which is 1. We repeat these steps until the heap size is 1, at which point we have array A sorted from lowest to largest. Now let's look at the code. The program I wrote is a C++ console application. The IDE I used is Visual Studio. First we have Quicksort partition definition. Below we have Quicksort procedure defined. It recursively calls itself 2 times on 2 subarrays after partition. Next we have Heapsort definitions. Variable heap size holds current heap size. Then we have left child, right child and parent of a node I. Below that we have max heapify procedure, which recursively calls itself. Below we have build max heap, which calls max heapify for every node other than leaf from lowest up to the root. Finally, we have our Heapsort algorithm definition. It calls build max heap procedure and later swapping root element with lowest leaf, then decreasing heap size by 1, and after that max heapify. Now let's see our main function. First we have random numbers variables definition. std random device def merge and twister variable and distribution, which is uniform from integer 1 to 100. The block of code following random number definitions calls Quicksort and Heapsort on 2 vectors with 100 random numbers each. Then it prints sorted vectors. Let's see if it works as expected and run the program. We see 2 arrays sorted. Now let's comment this fragment out. And let me explain further fragment of the code. Vector names contains header names of 5 columns that will be displayed on the console. These are row number, algorithm name, which is Quicksort or Heapsort, input array size, range of the random numbers that the array will contain, and finally execution time of algorithms. Next, we can see for loop that displays column names of a header row. Below that, there is declaration of vector of tuples called main_vec. Each tuple will contain strings algorithm name, array size, numbers range, and long duration of an algorithm measured in nanoseconds. Further in the code we see 2 for loops that iterate through variable I, array size, and second loop that iterate through variable j, which is numbers range. Array size I takes on the following values: 10, 100, 1000, 10,000 and 100,000. For each I value there is a j value that takes on from 10 to million with step multiplied by 10. Inside the second loop there is filling the vector called num to be sorted with uniform distributed random integers in range from 1 to j. The size of the vector is I. Next, we call Quicksort on a copy of vector num to be sorted. Quicksort is surrounded by 2 time points, begin and end, whose difference is duration of an algorithm in nanoseconds. Then we have tuple creation and push back this tuple to main_vec. Next we have the same block of code as for Quicksort with difference that it calls Heapsort. Finally, there is a for loop that outputs tuples of main vector which contains running times and info for Quicksort and Heapsort. Let's run this program. It will take a while. For array size 10, Quicksort is faster than Heapsort up to 2 times. Only for numbers range 1 to 10, Quicksort is the execution time of Quicksort is the same as Heapsort. For the larger ranges, Quicksort takes from 400 nanoseconds to 500 nanoseconds, while Heapsort runs from 800 nanoseconds to 1000 nanoseconds. For array size 100, Quicksort is faster for all numbers ranges, nearly 2 times than Heapsort. For array size 1000, Quicksort is slower than Heapsort for range 1 to 10, 2.5 times slower. For the bigger ranges, Quicksort is more than 2 times faster than Heapsort. Quicksort takes around 120 microseconds, while Heapsort more than 250 microseconds. For array size 10,000 and range 1 to 10, Quicksort is more than 15 times slower than Heapsort. For range 1 to 100, Quicksort is 2 times slower than Heapsort. Starting from range 1 to 1000, Quicksort is faster than Heapsort. Taking around 1.5 millisecond, while Heapsort around 3.5 milliseconds. For array size 100,000 and range 1 to 10, Quicksort is slower than Heapsort more than 100 times. For range 1 to 100, Quicksort is slower than Heapsort more than 10 times. For range 1 to 1000, Quicksort is slower than Heapsort 1.5 times. Starting from range 1 to 10,000, Quicksort is 2 times faster than Heapsort. In conclusion, Quicksort is faster than Heapsort when array range is more than 1/10 of array size. For example, for array size 100,000 and range 1 to 10,000, Quicksort is faster. For row ranges compared to array size, Quicksort is slower than Heapsort. To run this program for large array size, it's necessary to increase stack size. In project properties, linker, and then system, increase stack size to 4 megabytes. Another thing is that Quicksort in worst case runs in n square time, while Heapsort in n log n time. That's all. Thank you for watching.